Okay. Now, from last time, we talked about Euler's method. For general first order ODE. Okay. Now, so this is an example of what's called a one-step method. So now I'm going to talk about one-step methods in general. Where as long as yn plus h, and we have some function phi that has its arguments tn, yn, and h. Okay. So for instance, for Euler's method, your function phi is just going to be f. So quite simple, but we'll see other one-step methods where the function phi is much more elaborate in order to get high order accuracy. All right. So to help analyze accuracy, I'm going to define a very important concept, the local truncation error. Okay, so that would be Tn is now, keep in mind the notation from last time. Y of t n refers to the exact solution, and y sub n is the numerical solution. In both cases, at time tn. So you see what's happening in the definition of the local truncation error. Basically, I'm plugging in the exact solution into the numerical method. And since yn is supposed to approximate ytn, the local truncation error ought to be small. Smaller the better. Okay. But I've divided by h in this definition to give us something that more closely resembles the original ODE that you're trying to solve. So, if I take the limit as n goes to infinity of Tn of h in such a way that T naught plus nh is equal to some fixed t. So in other words, n is going to infinity, but h is going to 0 in such a way that the product n times h is constant. Okay. So the reason for that is, so in other words, this is some fixed time. t. Whereas Tn plus 1 is Tn plus h. So even though this is remaining fixed, this is not. It's getting closer and closer to Tn. Okay. All right. So if I take the limit of this as h goes to 0, n goes to infinity in such a way that we're dealing with a fixed time, what happens to this?
Become a smaller.
Well, h is going to 0, but this time is approaching this one.
So it's indeterminate form, like,
Well, technically indeterminate form, but what, like I said, this one actually is going to have a limit that exists. In fact, I can go ahead and rewrite this as y of, since Tn, in this limiting process, Tn is supposed to equal a fixed time t, minus phi of t, y of t, and h. So as h is going to 0, n is going to infinity together,
Wait, H is going to. Wait, repeat that.
h is going to 0, n is going to infinity, but they're doing so in such a way, they're going to their respective corners in such a way that n times h remains constant. So for instance, you get like maybe h is like 1 over n or something like that. Okay, so to take this limit, do you look at it either way? What's going to happen? So actually here I've taken n out of the picture.
But you're just saying that approaches 0.
Yeah, so what is the limit of this as h approaches 0?
0.
No.
Wait.
What's the limit?
Oh my god, no.
What did you say?
What is the limit of that?
Yourself one more time.
What?
Repeat
0
yourself one more
over
time.
0, then you need to get.
Alright, I want the limit of this as n goes to infinity, h goes to 0, but in a way that nh remains fixed. So that way we're dealing with a fixed time t here. But to help you guys, I rewrote it this way, so that to reinforce that Tn remains fixed.
Derivative, right?
Yes. Because why would you call it? Were you calling it 0?
I think so. I don't know what I was hearing.
Yeah, because it's 0 over 0.
And then you said the
Definition of derivative.
Yeah.
So yeah, we have y prime of t over here, and then this, we don't know what this is, but we're just taking a limit as h goes to 0, so we're just going to have phi of t, y of t, and 0. But what is y prime equal to?
F
Yes.
of ty.
Yeah, so f of t, y of t, minus this. Okay. Now, I'm doing this limiting process because as h goes to 0, your numerical method should produce the exact solution. So this should be, so this equation, this difference equation should be consistent with the original differential equation. So, so this expression here should be 0. So that's what we have to make sure of. That if a local, because basically the local truncation error, you can think of it as a measure of the error that's committed during a single time step. Well, as your time steps are shrinking, the error you're committing during a single time step should get smaller and smaller. So as h goes to 0, there shouldn't be any error at all. So, so this criteria here is okay. So this leads me to a definition of a very important term that the one-step method is consistent with the original ODE, y prime equals f of t y. Oops, I didn't mean write Euler's method. I wanted a general one-step method. Sorry about that. All right, so general one-step method is consistent with the ODE if, for whatever function phi you have that describes your method, if you plug in h equals 0, f should pop out. So, so that's your criteria for consistency. Basically, you're saying that in a limit as h goes to 0, your numerical method is consistent with your differential equation. Otherwise, there's no chance that your numerical solution will resemble your exact solution. Okay. So, question on the definition of consistency. Now, right now, the only one-step method we've seen is Euler's method. We'll see other one shortly. And here, you can definitely tell it's consistent because phi is f in that case. Now, so for a consistent method, this local truncation error is going to 0, but this local truncation error generally depends on some power of h. Like in Euler's method, it's a first-order method, so it's proportional to just plain old h. Higher-order methods will be proportional to h to some power, like h squared or h to the 4th. So we like to see local truncation error that's a highest power of h as we can get. But in all cases, we must have this to ensure that that local truncation error is at least going to 0 at all. Okay. Now, so that's one condition that we need to show that a method, a one-step method, can possibly converge. Because convergence is what we really care about. But to get to convergence, we have a couple, like, I guess, gateway concepts, and consistency is one of them. Another criterion is stability. So again, a general one-step method
Dr. Ivers,
yeah.
you gotta move your computer.
Sorry, what?
Computer.
Dang it. Okay, thank you. Okay. So this general one-step method is stable if your function phi that defines your method is Lipschitz continuous in the y variable. So in other words, we evaluate this phi function at two different points where only the y is changing, then there's some constant I'll call L sub phi. You can think of L sub phi as being a bound on the partial derivative with respect to y. So the change in phi is bounded by this constant times a change in y, where t and h are held fixed. Okay. Now, the idea is, if you have a method that is consistent and stable, then it is convergent. So consistent means that the error committed during a single time step goes to 0, as a time step goes to 0. Stable just means that your solutions have the correct qualitative behavior. Like if your solutions are supposed to, decay or maybe have some exponential growth allowed, but again a controlled growth rate, that a stable method will honor that. You don't have solutions that blow up to some unreasonable degree. Convergent is what we really care about. That I gave a definition last time, so I'll repeat it here. That the limit that then goes to infinity of the maximum over all time steps of the difference between your exact solution at a certain time and a numerical solution at the same time must be 0. So that's what convergent means. Okay. Consistent just means that the local truncation error goes to 0 as h goes to 0. And stability just means your phi function is Lipschitz continuous. Okay, so basically it has a bounded derivative with respect to y. So it's similar to what you see what are called well-posed problems. A well-posed problem has a solution, it's unique, and it depends continuously on the data. So a small change in the data won't cause a large change in the solution. So here by requiring that phi be not just continuous, but Lipschitz continuous, this prevents the situation where you have a small change in the problem data leading to a very large change in the numerical solution. Okay. So I'm going to now prove that for a general one-step method, if it is consistent and stable, then it is convergent. And it's going to be very similar to what I did with Euler's method. At least the difference is, with Euler's method, we knew what the local truncation error is. It was like h over 2 times y double prime. So we knew it went to 0. And stable happened because we are assuming that f was Lipschitz continuous. And for Euler's method, phi is f. So phi was Lipschitz continuous too. So I didn't really talk about those concepts of consistency and stability, but now for general one-step method, I need to. Okay. Now, I'm going to define, I used this before, but I never gave it a name. The global error I use the same notation as before. E sub n is your exact solution at a certain time minus the numerical solution at the same time. All right. I don't actually have a proof in my notes. I just say it's just like a proof of Euler's method. Well, it is true. It really does work out that way. But to give you a general idea as to why, for a Taylor series expansion, well, okay, I have really not, actually I'm not doing a Taylor expansion here. I'm using the definition of local truncation error. All right, so this is your LTE, local truncation error. So again, this algebraic rearranging of a definition I gave earlier. The numerical solution, I was going to write out the method here. Okay. And then you subtract the two. Well, this difference is just En plus 1. This is En. And then here I have a difference of 5 values. Local truncation error. So then what I can do is I can bound the absolute value so I have En times 1 plus h, because here I use a Lipschitz continuity, and I get L phi. All right, because this is this difference of 5 values is bounded by the Lipschitz constant times the difference in y values. But what's the difference in y values? It's En again. So if you look back at the proof I did last week for Euler's method, it works exactly the same way. But I still have the local truncation error. And what I did last time was you get a partial sum of a geometric series and so forth to come up with a bound for the error in terms of errors from previous time steps. So following that same proof, what you end up getting is En is less than or equal to e to the L phi. So basically, if you mimic what I did last week for Euler's method, you'd see, so I'm not going to do it here because it's not really all that interesting. I don't want to fall too far behind. So you have that expression, which doesn't depend on h at all, times the maximum over all time steps of the local truncation error. And the thing is, this goes to 0 as h goes to 0. So the stability of a one-step method allowed us to do this. The consistency of a one-step method allows us to say that this goes to 0 as h goes to 0. So as a result, the error goes to 0 as h goes to 0. All the errors go to 0. Therefore, it meets the definition of convergence, because we want the maximum of En over all time steps to go to 0. As n goes to infinity, h goes to 0. And from this, we see that it does. All right. So by defining one-step methods in this generic way and requiring this stability condition, really the proof is hardly different at all from a proof for Euler's method. Okay. questions about this? So to associate how this proof would go with the previous one on Euler's method, I'll fill in some particulars. Okay. So with Euler's method, the function psi is just f. The local truncation error is h over 2 times the second derivative of the solution at some unknown time. See, there's actually a mistake in the notes. In the notes I have f double prime. It really should be y double prime. Not sure what I was thinking here. And this is at some unknown time between Tn and Tn plus 1. Okay. All right. So what that means is your error, your global error, can be bounded by some constant k times h. The important thing is that it's h to the first power is the bound. So, so we say that Euler's method is first order accurate. Or we say that the error is order h, or big O of h. So not all that, not great, but it works, and it's certainly a simple one to implement. Okay, so more generally, as order of accuracy P, if the local okay. Well, I'll resolve this in a moment. Local truncation error is bounded by some constant times h to the p. Now, here I'm talking about the local error, here I'm talking about the global error. In fact, both are true. In fact, that's why the local truncation error has been defined in the way that I did, where I didn't just plug the exact solution in the numerical method, I rearranged and divided by h. That way, and actually this would, if you were to go through the whole proof, for convergence of a one-step method, and you filled in that what the local truncation error was for whatever method, or bounded by kh to the p, and actually you can see it from the final error bound over there. What is the global error? The global error is bounded by some constant times the local truncation error. The thing is, we define order of accuracy in terms of a local truncation error because that's easier to get a hold of. For typical one-step methods, you come up with a fairly precise formula for local truncation error. Global error, don't even bother. And you come up with a bound for it, but that's really all you can do. But because of how consistency and stability imply convergence, the order of accuracy is the same no matter whether you're talking about local truncation error or global error. Okay, but I still kind of goofed. My notes are supposed to have local error here. But but the statement is correct either way. So, okay. All right. So, so we're going to see higher order accurate methods. In fact, starting now. I saw it in text. I thought maybe it's Vivian, but nope. Okay. Move a computer. Okay. So now I'm going to talk about very different sort of one-step method. Implicit method. Okay. Now, if I have y prime is equal to f of ty, I can rewrite that by, if I integrate both sides with respect to t, I can say y at time tn plus 1 is y of tn plus the integral from tn to tn plus 1 of a derivative, which is f. Yes. Okay. So this is the integral form of the ODE, and this is exact. I haven't performed any approximation yet. But now I will. Suppose I want to approximate this integral by the trapezoidal rule that we saw several chapters ago. Okay. So what comes out of this is the trapezoidal method. So what's the trapezoidal method? You take the width of your interval, which is h, you divide it by 2, and then you have the heights at the beginning point and the ending point. So that's the trapezoidal method. Now, okay. So now what I'd like to do is find a local truncation error of this method. So for a definition of that, I have, all right, so y of tn plus 1 minus y of tn over h minus whoops. Okay. Now, I can write this as, I'll factor out a 1 over h, and then, what is this? Y plus 1 minus yn, y of tn. That's this integral. Oh, that should be an s, because s is my variable of integration here. Y of s. Okay. Minus, oh, sorry, I goofed over here. This should be exact solution, y of Tn, and this should be y of Tn plus 1. Okay. So then I have h over 2, and evaluate the integrand at time Tn. And Tn plus 1. Okay. Now, this local truncation error, what do I have? I have 1 over h times an integral minus the trapezoidal rule approximation of that integral. So this is 1 over h times the error in the trapezoidal rule. Well, we have an error formula for that from before, so we can just use that. So we get 1 over h. The error formula is minus h cubed over 12 times the second derivative of the integrand of f, but that's the same as the third derivative of y. At some unknown point. So we simplify this, we get minus h squared over 12 times third derivative. Okay. So this is the local truncation error in the trapezoidal method. And notice it's proportional to h squared. So we can say that trapezoidal method, unlike Euler's method, is second order accurate. Okay. Now, because the error is proportional to h squared, it's definitely going to 0 as h goes to 0. So we can definitely say that the trapezoidal method is consistent. So if we want to show that it's also convergent, all we have to do is show that it's stable. Show that the function phi for this method is Lipschitz continuous, and then we're good to go. Because it's already been established that one-step method that is consistent and stable is convergent. So we don't have to go for that tedious proof like we did for Euler's method. And for a more complicated one-step method, that'd be a huge pain. Okay. So let's take a look at stability. Okay. So if a function phi, in this case, is actually, by definition in the notes is a bit off, but I'll fix it here. So we plug in, here's what we have for our, you think of this as our T and Y n. So let's go ahead and plug that into F. So right now we have half the phi function for Euler's method, but then the other half we do something different. F of T plus H. Okay, this is odd. I actually have a stability proof for the wrong method. because there's two trapezoidal methods. There's this one, that's an implicit method. There's also a variation of it that's explicit trapezoidal method, and that's the one I have here in my notes. Because I need a way to describe yn plus 1. Okay. I've done this before, it hasn't failed me yet. I'm just going to see if I can fix this on the fly. Because, so yn plus 1, and we call the method, so if I were to fit that, so Tn is by T, Yn is by Y. We know how the T's relate, they're just different by H. Yn plus 1 would be Y plus H over 2 F of Ty plus, well, we would have like an infinite recursive loop here. And I don't, and the thing is I don't have a symbol for it. That's the problem. Okay. Unless, oh, wait a minute. Tn plus 1. This is what I get from my notes not being very clear. Oh, okay. Because the thing is, I can't just rearrange that and solve for yn plus 1. That's really the problem with implicit methods. Okay. But I need a good definition of phi to work with. Okay, dang it. All right, can I borrow a textbook for a second? It might not even be in there, because I think if these notes are adapted for a different textbook. So to fix my textbook though. Okay. All right. Phi is. That's strange. They do the very thing that I said was, oh. That's really weird, and I don't think I like it, but I think that's all I can do. So, okay.
I was trying to Google it.
Okay. All right. So, because you're trying to fit this into the form, y plus 1 is yn plus h phi of Tn, Yn, H. So what's done is here, so my phi starts out with this, that's the straightforward part, and then here's the problem. I need f of tn plus 1, which is fine, and then I need yn plus 1 here. So what do they do? They just take this and substitute it in here. In other words, it's a total cop-out in a way, because if anything, this is kind of a strange way to describe its function. It's not, because say its arguments are tn, yn of h. I guess that technically that's all the input that a one-step method has. So that's yeah. Okay, so this would be y plus h phi of t y h. All right, so all of this is yn plus 1. All right, and the thing is, that would be the case for any one-step method. Gotta really hope that none of my colleagues ever watch this.
Always edit it out.
What?
You can always edit it out.
Interesting point. But then I wonder why. No, because this, if I were doing the stability proof for the explicit trapezoidal method, that is exactly what I would have. So there's no difference between them. And that's what threw me off, because I do discuss the explicit trapezoidal method elsewhere, and I thought, maybe I had this written up for that, and by mistake put it in here. And I thought, well, this can't be right. But it turns out that even though the phis are different, but when you, yeah, that's, oh, okay. After I finish this, if I haven't used up all my time, okay, I'm falling further behind. This semester won't end early after all. I'll be able to explain the difference. Okay, so I can salvage this. No, it's just total brain fart, but now I remember, well, what I need is, I need to go fix my notes to explain better what I'm doing. And at least you guys are seeing, whatever you have for your general yn plus 1, your general one-step method, that's what you put in here if yn plus 1 appears in your method, on the right side. Okay, so that's how you handle this for proving stability in general. Okay, so, well, it's Monday, it's been a long day, so whatever. So if any of my colleagues do watch this, they can find me. Okay. So, to show Lipschitz continuity. Okay, it doesn't apply to Dr. Schroeder, but okay. So I need to change the y variable. So I have t y2h minus phi t y1h. So that's going to be 1/2 f of t y2 plus f of t plus h y2 plus h phi of t y2h, okay, minus same thing at y1, and we're assuming all along that f is Lipschitz continuous. So f of t y2 minus f of t, because we would need that for a well-posed problem. So that's equal to L. So plane L is Lipschitz constant for f. So we're going to make use of that here. So what do I have? This is less than or equal to 1/2. Now here we have a difference of f values. So I'd have L, y2 minus y1. And then here I have plus L again times the difference of these two y values. Y2 minus y1 plus h phi of ty2h minus phi ty1h. Okay. So this difference of phi values is exactly what I have over here. So what I could do is I can rearrange this. I can move this to the other side. And so what I have is, I'll leave some space here deliberately. This difference of phi values is less than or equal to 1/2. Oh, I actually have two of these terms. So in fact, yeah. So I can combine it into one, and I just get L. Y2 minus Y1. And what I have on the other side is 1 from here minus 1/2 H L. Okay. So this got moved to the other side. Everything else stayed put, and it got combined or simplified. So any questions about this? This is really the key step right here. So I can just divide by that now. So the Lipschitz constant for L phi is equal to 1 over 1 minus, L over 1 minus H over 2 times L. Now, it's important that H over 2L be less than 1. So as long as H is sufficiently small, there's a valid Lipschitz constant. So we can say that the method is stable. Okay.
Excuse
Yeah.
me. How we can say that it's stable?
What?
How we can say it's stable?
Oh, well, stable means a phi function from a method has a Lipschitz constant. So yeah, because if I were to divide by this, I'd say difference in phi's is bounded by this constant times the difference in y's. And it's just that the Lipschitz constant is going to be a little bit larger than what we would get for Euler's method. So during, okay. Now, oh, okay. Now the thing is, this method, the trapezoidal method, is implicit because yn plus 1 is on both sides of the equation. All right, so we're just plugged into F. That's the key here. So any method of that form, where you have your solution at the new time, both sides of the equation, that's an implicit method. Okay. So what that means is you have to solve a nonlinear equation. For yn plus 1. Using any root finding methods like Newton's method or secant method, things like that. One of the nice thing is you always have a convenient initial guess, yn, and of course the smaller your h is, the better an initial guess that will be, or yn plus 1 from an explicit method. Because you can compute that relatively quickly and then have an even better initial guess. What a lot of methods do in practice is they use Newton's method but only carry out one iteration. Because if you already have an initial guess, that's really good. And then Newton's method is quadratically convergent. So if you're already close, that will get you that much closer. Plus, there's going to be some error anyway. So what's the point of solving a system of equations to high accuracy if that error is already dwarfed by error from other sources, like a local truncation error of a method. So this is not as impractical as it seems. Okay, now here's another implicit method, a simpler one actually, backward Euler. Is the same as Euler's method, except you plug in time n plus 1, and yn plus 1, into f. So that's really the simplest implicit method. And then I want to contrast, here's an explicit method. The explicit trapezoidal method, very similar. It's also called Modified Euler. And that would be yn plus 1 equals yn plus h over 2. So it starts out looking exactly like the trapezoidal method I was dealing with. So then we get plus f of tn plus 1. And instead of putting yn plus 1, what we do is we use the Euler's method approximation of yn plus 1. Okay. All right. So this method, backward Euler, is first order accurate. Whereas the explicit trapezoidal method, like its implicit relative, that is second order accurate. And to resolve how I got thrown off earlier when I was dealing with a phi function for the implicit version of a trapezoidal method, for this method, phi of t y h is equal to 1/2 f of ty plus f of t plus h y plus h f of t y. Okay, so on this board you have phi for the explicit trapezoidal method. On the other board you have a phi for the implicit trapezoidal method. Where do they differ?
The last part?
Yeah, right here. Here I just have plain old f. Over there I have phi again. So, but when you have an implicit method, phi is recursively defined. You can't write down a formula for it because of the implicitness, but in this case you can. Okay. Now, okay. Time, not very good. I guess as a segue into the next topic, which I won't really be able to get into, the explicit trapezoidal method can be written this way. I'll define K1 to be HF of Tn Yn, and define K2 as HF of Tn plus H, and then I have Yn plus, I have this, but this, I have to put that there, but that is the same as Yn plus K1. So once I have both of those, I could say Yn plus 1 is equal to Yn plus 1/2 K1 plus K2. And this is a very simple example of what is known as a Runge-Kutta method. Okay. Which are designed to have very high order accuracy. Here we have two evaluations of f. So this is called a two-stage method. So whenever you have an evaluation of f at some point, that's called a stage. So this is a two-stage, second-order Runge-Kutta method. And so on Wednesday, I'll get into how you can derive these kind of methods in general, and a higher order example than second order. Okay. But yeah, certainly the concept of implicit methods is very important because for various PDEs especially, when you discretize them as a system of ODEs, often implicit methods are used to solve them because of issues of explicit methods where you need a very small time step. That's something when I get closer to the end of a chapter, we'll discuss more. So, yeesh.
Can you write the same thing for implicit?
What?
Phi? Can you write the same thing for implicit?
Okay, this phi compared to that phi,
Mm-hmm.
but they're not quite the same. They're almost identical. The only difference is right here. Here I have f, but here I have phi.
So if I put phi here, then it will be for implicit.
Yeah. Yeah, when you define the phi function for a particular method in terms of itself, that's when you get an implicit method. But at least here I can define phi explicitly in terms of f at different points. Alrighty.